Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be looking at some topical past paper questions for kinematics. That's paper 1 kinematics, the multiple choice for Cambridge A-level physics. Now I'm going to be using the Papa Cambridge topical questions, and as always, I'll leave a link in the description of the video so that you can use these questions to help you prepare for paper 1 for A-level physics. Now, paper 1, although it's only AS physics content, that is the first year of A-level physics content, and it is multiple choice, this paper can be quite tricky. It can also be make or break. As although there are only 4 options, usually the 4 options are all common mistakes for that kind of question. And so it's very easy to make errors when deciding to choose an answer, as we'll see as we go along. So I'm doing the kinematics questions, which are from 173 onward, and we're going to do questions 173 to 183 in today's video. Now, in kinematics, remember kinematics, we said recently in our crash course that kinematics is the study of motion when we don't really care what's causing the motion. We just cared about the motion on its own. So the first question, 173, comes from the March 2020 exam. Subject code is in front, 9702. It comes from question paper 1, variant 2, and it's question 7. We're told that a car moves with uniform acceleration along a straight road. Oil leaks from the car at the rate of 1 drop every 2 seconds. The diagram shows the distances between 3 successive oil drops on the road. So we have the first drop, 2 seconds passes, this 9 meters. Later we have the second drop, another 2 seconds pass, but now 12 meters pass and the third drop is visible. This is uniform acceleration, not uniform velocity. And we are asked to find the acceleration of the car. Now, believe it or not, all of these 4 answers are common errors. So it's very easy to make a very small slip up, a small mistake, and see one of these answers on your calculator, and immediately that confirmation bias in your mind tells you that that must be correct, because I must have done something correct to get an answer that's there. But be wary of this. As a good scientist, you have to make sure you don't fall into that trap. So what happens? Well, initially, let's say I'm traveling at some speed, u1, I don't know what the speed is. And then by the time I'm at the second oil drop, I'm traveling at a speed v1. And by the time I reach the third oil drop, the speed is v2. And the separation in time of these events is 2 seconds between each event. Now again, I'm going to use methods that are a bit long-winded. You're going to try and find methods that are a lot quicker and smarter because you don't have a lot of time, and 40 multiple choice questions is actually quite a lot for 1 hour, 15 minutes. But I'll show you how to solve these problems sort of like in the first principles way, and then you can figure out, well, quicker ways to do them without as much writing as I would do them. But what I would do is I'd say, well, for the first 9 meters, I'm going to use an equation of motion, uniform acceleration, so I can use a kinematic equation of motion. That displacement S1 is ut plus a half at squared, where I'm only considering the first motion, the first 9 meters. So that value 9 is equal to 2, where t is 2 seconds, times the initial velocity for that first portion of the motion. I don't know what it is, so I'm going to call it u plus 2a. Why do I say 2a? Because t again is 2 seconds. 2 squared is 4, a half of 4 is 2. So I get 9 is equal to 2u plus 2a. Now I've got a single equation with 2 unknowns, so I can't solve for the acceleration from there. But what I will do is use my second piece of information, and I'll say that S2 is ut plus a half at squared again, but I'm now going to do this for the full 21 meters. So I'm going to do it for the 9 plus 12, for the entire, from u1 all the way to v2. So for 21 meters. And so I get 21. And the reason I do this is because the initial velocity u is the same for the first 9 meters and for the whole 21 meters. So I get 4 seconds having passed times the same u plus 8. So 4 squared is 16, a half of 16 is 8 times a. So you see what I've done there. I've got the same acceleration because acceleration is uniform, and I've got the same initial velocity because my starting point is the same. And we'll call this equation 2. And now it's just a simple matter of doing the mathematics. So if I take equation 2 and I subtract twice equation 1, 2 times equation 1, then what I get will be, and you can do the mathematics to make sure that I'm correct, 3 is equal to 4a. So the uniform acceleration is 0.75 meters per square second. So this one corresponds to option A. Again, you'll have an answer sheet in front of you, so make sure you are shading the letter A on the answer sheet in an HB pencil, nice and dark. But my suggestion would be, when working in paper 1, maybe ring the answers that you are most confident with a pencil on the question paper, and then do your shading towards the end when you're confident with all your answers, so you don't do too much erasing on the answer sheet itself. So that was question 173. Next is question 174 from March 2020, question paper 1-2, and it's question 9. The diagram shows graphs of various quantities plotted against time for an object dropped from a stationary balloon high in the atmosphere. And we want to know which statement could be correct about these graphs. Graph 1 is acceleration against time, and 3 is resultant force against time. Graph 1 is acceleration against time, and graph 4 is resultant force against time. 3 is acceleration against time, and graph 1 is velocity against time. And D says 3 is acceleration against time, and 2 is velocity against time. So I don't have to think about all the quantities plotted against time. I'm literally only asked, I only can see an acceleration, resultant force, velocity. So guess what? I'm going to draw those 3 graphs and see what they look like. So there's an object dropped from a very high position. We're not told to neglect air resistance. When the object is dropped, we don't know what object it is, but it has a weight acting downward. That's a force due to gravity acting downward, and it's moving downward, so at some point it'll have a speed v, and upward will be air resistance. Since it's falling downward, air resistance will oppose the motion and act upward. Now, what do we know about air resistance? Well, as speed increases, the air resistance F increases as well. And we do know it doesn't increase linearly. In fact, it increases quadratically as a function of v squared, the air resistance. Now, at any time, the resultant force is the weight minus the resistive force, the air resistance, and this, according to Newton's second law, must equal to ma. So this is the resultant force. Resultant force is W minus F. But F gets bigger and bigger and bigger and bigger, and at some point, F and W are the same. When your air resistance matches your weight, what happens is that you start to move at constant velocity, or terminal velocity. So go through terminal velocity if you are a little bit confused. But what happens is F net and acceleration A both decrease, because F is equal to ma. So actually, their 2 graphs will be sketched almost identically. The resultant force and acceleration graphs will look the same with time, besides the values being different. So if I were to sketch a graph of velocity versus time for a freely falling object with air resistance, as the object gets faster, or as it falls further rather, its overall speed increases, but then increases at a much slower rate as the net force gets smaller and smaller and smaller. So the gradient of this graph, which is acceleration, gets less and less and less, and eventually becomes 0. And at that point, the object reaches terminal velocity. And terminal velocity means it's not going to get any faster. So we usually call that VT. So that's a sketch of velocity versus time. Again, this, you wouldn't be doing all this working. This would be from the top of your head, and you could do this in a very, very, very short space of time with the knowledge of terminal velocity. Now, the net force decreases until it eventually reaches 0, because when the net force reaches 0, the object is falling with terminal velocity. And similarly, like I said, net force and acceleration will be sketched almost identically. The acceleration versus time graph is the same. It eventually will reach zero because the object will stop accelerating when the weight and the friction, air resistance rather, balance out. And so if I look at this graph, the one that matches these the best is option C. So option C says graph 3 is acceleration against time, A against time, and graph 1 is velocity versus time, which I can see matches the graphs that I've drawn. So spend some time practicing sketching what graphs would look like for terminal velocity and for other scenarios, other common scenarios in kinematics and projectile motion as well. The next question is question 175. It is from the summer exam of 2020. That's May-June 2020, question paper 1-1, and it's question 6 from the paper. We're told that the velocity of an electric car changes as shown. What is the acceleration of the car? To be honest, I think the only thing that's the issue here is that we are given a graph of kilometers and, well, given a speed in kilometers per hour versus seconds, but they want the acceleration in meters per square second. That really isn't going to trouble us, is it? A is delta V by delta T. You can check for yourself that I can choose values of velocity from this graph, any two values. 105 minus 0, I'm going to use the extreme values, divided by 4 minus 0. And now I have to convert units. So what I get is I calculate this, I will get 26.25. Now the units are important here. It's going to be kilometers per hour divided by a second. So kilometers per hour second. Not very nice, but we basically want meters per square second. So now the hour second, I have to get rid of the kilo and I have to get rid of the hour. So I wrote it like this so that I can get rid of the units and I can see how they disappear. Now I want to get rid of the k, so I'm going to have a k in the denominator as I already have one in the numerator. So I can write it as there is 1,000 meters for every kilometer. Okay. So I can get rid of the kilometers now. Now I have meters per hour second, which is quite messy. So I want to get rid of the hour. So I need an hour in the numerator, 1 hour. How many seconds are there in an hour? 3,600. And so I can get rid of the hour as well. So basically I'm multiplying by 1,000 and dividing by 3,600, or dividing by 3.6. And what I get is that the acceleration will be 26.25 times 1,000 divided by 3,600, 7.3 meters per square second. I have a second here and a second here, so there's 2 seconds in the denominator. That's where I get meters per square second, and this corresponds with option D. Also, what you could do is calculate the change in velocity in kilometers per hour, convert that to meters per second, and then do this calculation. Basically doing the calculation in the numerator for this problem. But again, that's completely up to you how you want to do that. But it's not going to trouble you. Just converting units, I think you should be okay with that. The next question is number 176 from summer 2020 exam, question paper 1-1, question 7 from the paper. We're told that a projectile is fired from point P with velocity v at an angle theta to the horizontal and lands at point Q, a horizontal distance r from P after a time t. The acceleration of free fall is g, air resistance is negligible. Which equation is correct? And we're given 4 equations. R is vt cosine theta, R is vt sine theta, R is vt cosine theta minus a half gt squared, and R is vt sine theta minus a half gt squared. You do not need to memorize the range equation. The range equation is not one that I would expect you to memorize. It's something that if need be, you can derive it, in fact. But again, here we don't need to do any complicated mathematics. So I have the object being sent out with some velocity v from the horizontal at an angle theta. I want the horizontal distance r in terms of v and t and theta. And so what I can see is that from P to Q, the horizontal component, now remember there's no acceleration in the horizontal direction, and we only want the horizontal distance. So the vertical distance doesn't need to come into this at all. In fact, none of the vertical quantities need to come into this at all. So the distance is the constant velocity in the x direction times the time, which they told us is t. We don't need to worry about what the vertical component is doing. And Vx, as we look at it, is V cosine theta. So that's V cosine theta multiplied by t, which is Vt cosine theta, which corresponds to option A. So we can do that without, I think they were just trying to make sure that you were not including the vertical component, which we didn't need. In the horizontal direction, there's no acceleration. So distance is speed times time. Speed is v cosine theta, and that will remain v cosine theta for the entire motion since we are ignoring air resistance. Ignoring air resistance is also an important thing to mention there. The next question is from the summer 2020 exam, question paper 1, variant 2, and it's question 5. We're told that a stone is dropped from a height of 20 meters above water. The graph shows the variation with time of the velocity of the stone. And we want to know which statement describes the approximate position of the stone 4 seconds after it is dropped. Is it 10 meters above the surface of the water, 10 meters below the surface of the water, 20 meters below the surface of the water, or 30 meters below the surface of the water? Now, basically, you can see this graph is made up of a triangle and a rectangle. And let's take this 2 seconds at a time. Let's see what happens to the stone. We can sort of look at the graph and tell immediately what's going to happen. I mean, it's moving with constant acceleration. That means it's in free fall. And suddenly its velocity drops and then moves constantly. So that kind of makes me think the stone hits the water after 2 seconds and then starts to move with constant velocity in the water because there's an upthrust acting on it that balances its weight. But let's do the mathematics and make sure it really is under the water. So for the first 2 seconds, we have that the displacement covered by the stone is the area under the graph. So if you're thinking calculus, you're thinking the integral. If not, you're simply thinking that a velocity time graph, the area underneath that graph tells me the displacement of the stone. So if I only think of the first 2 seconds, I have a triangle. So I'm going to shade that triangle. And so that's a half base times I height for the area. That's a half times 2 seconds times 2 meters per second. Oops, sorry, 20 meters per second. And this is going to give me 20 meters. So what happens in the first 2 seconds, it reaches if it's 20 meters above the water surface and it falls 20 meters, it reaches the surface of the water. So our actual initial thought process was correct. And then what I'm going to do is, let me just change colors for this. I'm going to consider the next 2 seconds. So now I know it reaches the water surface. What happens in those next 2 seconds? The displacement in the next 2 seconds is the area from 2 to 4 seconds, that area of the rectangle. And that's a constant 5 meters per second multiplied by 4 minus 2. The width of that rectangle is only 2 seconds. Again, you're not going to be writing all of this down. You can probably do this in your head. And this is 10 meters. So basically, I don't have to add these two together. I can see that the stone now moves 10 meters below the surface of the water. So it's now 10 meters below the surface of the water, which is option B. Again, I did a lot of working for this, which you don't have to replicate. But if you want to make sure that that small errors don't come into your calculations, make sure you're just putting some pen to paper. It would be helpful in the long run. The next question is 178. It comes from summer 2020, question paper 1, variant 2, and it's question 6 from that paper. Now here's an interesting one. We're told that a car X is traveling at a constant speed U along a straight road. At time t is equal to 0, a second car Y is a distance d0 behind car X and traveling at a speed v in the same direction, and speed v is less than speed u. Time t is equal to 0, car Y begins to accelerate with a constant acceleration, and car Y overtakes X at a time t is equal to uppercase T. Which graph could best show the variation with time of the distance d between the cars? Okay, so remember, importantly, car Y is driving slower. It decides to accelerate, so the distance between X and Y is actually increasing until Y begins to accelerate, reaches the speed of X, and then increases its speed until it's over that of X. And obviously, with constant acceleration, its speed gets greater and greater until it eventually overtakes car X. So I'm going to just draw some very poor diagrams of cars. Believe it or not, this is a car. This is car Y. And it's initially moving to the right with speed v. And again, this is a very poorly drawn car. This is car X. It's moving to the right with speed u, and the separation between the cars is d0, as you can see in the diagram, and v is less than u. So initially, car Y is falling further and further behind car X. So firstly, Y begins to accelerate. Doesn't immediately accelerate to the speed of X. It has to accelerate and then gain velocity until it reaches the speed that the speed of car X is traveling u, so v is equal to u. So initially, what happens is that d actually grows to bigger than d0 for a very brief moment in time, while car Y's acceleration allows its velocity to match car X's. And so immediately we can see that the answer is going to be A or B. We could immediately eliminate C and D, because C and D shows that D is always decreasing, but A and B show that D actually slightly increases above D0 and then decreases, which is what's going to happen. Afterwards, V is always going to be greater than U because the acceleration is constant, and so V is always going to be bigger for all times. And then D is going to be less than D0. So still A or B, but what we know is that the acceleration is uniform. So the rate at which the velocity changes is uniform. This is a constant. And also we know that V is delta x by delta t, which means the rate at which the gradient of the graph of V versus t is changing must be constant. The rate at which the displacement is changing must be constant. So the rate at which the gradient of V versus t is changing must be constant. So what this means is our graph needs to have some uniformity in it, which again, you don't have to write all of this thought process out to understand. There's no uniformity in A. it decreases rapidly, and then the gradient changes. What we need is a decrease where the gradient is changing at a constant rate, and that is graph B. So you can see there was some logic. You had to eliminate C and D initially, and then you had to select from A or B. Well, A is for some reason changing at different rates, but B is changing at a constant rate. And so we can see that B is our correct answer. That's the variation of the distance between the cars, and at time t, car Y catches up to car X and overtakes it. Okay, so not so bad so far. Question 179 says the graph shows how the velocity of a ball varies with time from the moment it is hit vertically upwards from the ground. We want to know what the displacement of the ball is from the ground after a time of 3 seconds. Okay, so I'm just going to remove all of the previous question stuff that we have space to work with this problem. So question 179 says we are shown the velocity of the ball varying with time from the moment it is hit vertically upwards. So here's the ball at its lowest point, and then it's hit vertically upward, and we can see that it's hit vertically upward at time t is equal to 0 with a velocity of 20 meters per second. And what happens is that after 2 seconds, the velocity reaches 0. Now, this is not magic. Its velocity reaches 0 because it's at its maximum height. So remember, when an object or projectile is thrown, when it reaches its maximum height, its vertical velocity will be 0 instantaneously. And so it comes to a very short, for a very short rest, and then starts to fall again. And then at some other point, after an extra second, we have the ball some other height, and it's now traveling downwards, so its velocity is minus 10 meters per second. And what we want to calculate is the displacement of the ball from the ground. So it's height above the ground, basically. We'll call that S. And basically what S is, if we have a velocity time graph, is the area under the graph. I mean, you don't have to use area under graph. You could use your kinematic equations of motion, but this is a lot quicker. So I need the area under the positive side of the graph minus the area of the negative side of the graph, because first the displacement is upward and then the area is negative, which means the displacement is negative, which means the ball is coming down. And so what this is a half base times height, because it's a triangle, a half times 20 times 2 seconds, minus, now I'm going to change the color, minus the area under the negative portion of the graph, which is the negative displacement, which is a half times 10. I don't have to put minus 10 because I already have the minus sign in there, times 3 minus 2, which we know is 1 second. And so what we get is a displacement of 15 meters. And naturally, this will be 15 meters measured from the ground. So that's the question that was asked. What's the displacement from the ground of the ball? It's 15 meters, and that's A. So when calculating displacement from a velocity time graph, it's always quicker to use the graph itself and find the area. But you could use kinematic equations of motion. We know the initial velocity is 20. We know the final velocity is minus 10. We also know the time, we know the acceleration, we know so much we can easily calculate what the displacement will be. So a rare instance where there's very many methods of solving the problem, but we'll take it. We won't complain when we get a question like that. We are told next for question 180, this is from summer 2020, question paper 1, variant 3, question number 7, which says that 2 students each throw a ball horizontally from the top of a tower. The 2 balls are released at the same time. The first student throws a ball with a speed of 20 meters per second, and the second throws his ball with a speed of 10 meters per second. Assume that the air resistance is negligible and the balls land on horizontal ground. Which row describes the horizontal distance traveled and the landing times of the two balls on the ground? So they have same and different for the horizontal distance and landing times. Again, one of the probably less complicated questions that you'll find on kinematics. So I have student A throwing the ball at 10 meters per second, and student B throwing the ball with a greater velocity, 20 meters per second. But we are told that the balls are thrown horizontally. There's no vertical component to this velocity. So the initial vertical component for each ball is 0. So UAY and UBY, initial velocities are both 0. So what this means is that the time that they will take to hit the ground, even though they are launched horizontally, the time they'll take will be the same. TA is TB. However, the horizontal distance that they will travel will be different because B is thrown at a greater velocity. So ball A travels a shorter distance horizontally than ball B because it has a smaller horizontal velocity. So what this means is that this corresponds to option C, where the horizontal distances will be different, but the landing times will be the same. Again, not too tricky. We've seen problems that, a lot more complicated than that. Okay, so that's how we go about making sure that when two objects are sent horizontally, their landing times will be exactly the same because there's no vertical component of velocities. And so they will just fall at the same rate, which is g. The next question is 181. And this is from March 2019, question paper 1, variant 2, question number 3 from that exam. We are told that the speed of an aircraft in still air is 200 kilometers per hour. The wind blows from the west at a speed of 85 kilometers an hour. In which direction must the pilot steer the aircraft in order to fly due north? So they're only asking for the direction, not the required speed. Okay, so I'm going to draw my vectors here. I have a strong wind blowing in. It says from the west, so it's going to point east. From the west means it's pointing east. And it's 85 kilometers an hour. I can stick with kilometers an hour here. I don't need to use meters per second. And the pilot wants to fly due north. So the resultant vector, I'll call it FR, will be pointing north. The plane will eventually be flying north, but the plane must be pointing northwest. The plane will point northwest, but the wind will blow the plane slightly east, and so the plane will eventually move due north. And the speed of the plane is 200 kilometers an hour, so that vector is 200. Now, there's 90 degrees between east and north, which we know. And the angle that I'll label here will be this one, theta, because that's the angle of north, which is included in all of the answers. So I'm finding the angle relative to north. And basically what I need to do here is a little bit of trigonometry. So I get sine theta. Sine is opposite over hypotenuse. It's 85 over 200. So theta is the arc sine. Theta is the arc sine. Remember, when you want to find the angle, you use the arc sine of 85 over 200. Again, we don't have to convert units because we'll get the same ratio. And I get this angle to be 25.2 degrees. Now, 25.2 degrees as I've labeled it, which is pointing west off the north line. So we'll say it's west of north. So it's 25.2 degrees west of north. And that corresponds with option D, 25.2 degrees west of north. So in these kinds of questions, always draw your vectors, and then you can calculate your angles. We could, if we were asked, we could be asked maybe to find what the resultant speed would be, Fr. So what would be the final speed of the plane traveling due north? And the speed of the wind will affect that speed of the plane as it's trying to move due north. And so that was question 181. For this video, the last question we'll do is question 183 from the summer 2019 exam, question paper 1, variant 1, and it's question 3 from that paper. We're told that a particle has a velocity v at an angle theta to the horizontal. The components of the particle's velocity are vy upwards, or rather vv upwards in the vertical direction, and vh to the right in the horizontal direction. What are the expressions for the magnitude of v and the angle theta? Wow, okay, so this also is not too bad of a question, but again, it does require an understanding of vectors, which can be very tricky. So this is my vector. I'm throwing an object at some angle theta to the horizontal, and I'm throwing it with some velocity v. And then I can break the components of this vector, into a horizontal and vertical component, as we can do with any vector. I can break a vector, or I can write a vector as a sum of two perpendicular components. Perpendicular means they're at 90 degrees to each other. And then I have a nice right angle triangle. So I want the magnitude of v first. Well, Mr. Pythagoras tells me that v squared is vv squared plus vh squared, which means the thing I'm interested in is v would be the square root of vv squared plus vh squared. And that corresponds to a and b. So we can already eliminate c and d. But I do need the angle as well. I need the angle in terms of vh and vv. So vv is the opposite side, vh is the adjacent side. What has opposite and adjacent in it? It's the tan of theta. So the tan of theta is opposite over adjacent. It's vv divided by vh, which means the angle theta is the arctan of vv by vh. So again, you could have just looked at this problem without putting pen to paper, already knew what the correct answer would be. Certainly the magnitude of v wouldn't be difficult, looking at Pythagoras. The angle, maybe, if you need to draw a diagram, please draw a diagram, but this eventually corresponds with option B. So again, in case you want to mitigate having to erase too many times in your answer sheet, my suggestion would be to make a little ring in the question paper around the option that you're most confident in. If you feel like a question is taking too long, by all means skip it and come back to it later, but don't spend too long on a single problem. So we'll do more of these problems for the different topics in AS Physics to prepare you for paper 1. But if this video was helpful, please leave a like, leave a comment, subscribe to the channel if you haven't already. But that's all from me, Mr. K, for now. I'll see you again next time on Everything's Relative.